This is SpaceTime, Series 28, Episode 74, for broadcast on the 20th of June 2025. Coming up on SpaceTime, discovery of a record-breaking cosmic structure, a new way to build the red planet Mars, and scientists have struck gold developing new high-performance infrared nano antennas. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have imaged a record-breaking cosmic structure which is raising new questions about exactly what powers and re-energizes particles across the universe over time. The findings were presented at the 246th meeting of the American Astronomical Society, and they represent the largest known cloud of energetic particles surrounding a galaxy cluster ever seen. In fact, this massive structure spans nearly 200 million light-years, and it challenges long-standing theories about how particles stay energized over time. Instead of being powered by nearby galaxies, this vast region seems to be energized by giant shock waves and turbulence, which appear to be moving through the hot gas between galaxies. The structure is located some 5 billion light-years away in a massive galaxy cluster catalogued as PLCK G287.0 plus 32.9. The cluster has piqued the interest of astronomers since it was first detected in 2011. See, earlier studies spotted two bright relics, giant shock waves that lit up the cluster's edges. But in the process, astronomers missed the vast faint radio emissions that filled the space between them. Now, using new equipment, radio images are revealing the entire cluster is wrapped in a faint radio glow nearly 20 times the diameter of the Milky Way, and that suggests something much larger and more powerful is at work. The study's lead author Kamlesh Raj-Purohit from the Smithsonian Center for Astrophysics says astronomers expected a bright pair of relics at the cluster's edges which would have matched the prior observations. But instead, they found the entire cluster was glowing in radio light. And the thing is, a cloud of energetic particles this large has simply never been observed in any galaxy cluster ever before. The prior record holder was Able 2255. It spans roughly 16.3 million light-years. Deep in the cluster's central region, the authors detected a radio halo approximately 11.4 million light-years across. It's the first of its size seen at 2.4 GHz, a radio frequency where halos this large usually aren't visible. The findings are raising questions because they're providing strong evidence for the presence of cosmic ray electrons and magnetic fields stretched out to the periphery of the clusters. However, it remains unclear exactly how these electrons are accelerated over such large distances. Raj-Purohit says the very extended radio halos are mostly only visible at lower frequencies. That's because the electrons that have produced them have lost energy, they're old and have cooled over time. With the discovery of this enormous-sized halo, astronomers are now seeing radio emissions extending all the way across the giant shocks and beyond, filling the entire cluster. The study suggests something is actively accelerating, or at least re-accelerating the electrons, but the problem is none of the usual suspects apply. The authors think that giant shock waves or turbulence could be responsible, but they still need more theoretical models to find a definitive answer. The discovery provides astronomers with a new way to study cosmic magnetic fields, one of the major unanswered questions in astrophysics. And that could help scientists understand how magnetic fields shape the universe on the larger scales. It all means that scientists are now starting to see the universe in ways they never could before, and that means rethinking exactly how energy and matter move through the larger structures. Observations using NASA's Chandra X-ray telescope have revealed a box-shaped structure, a comet-like tail, and several other distinct features in the cluster's hot gas. And all that suggests the cluster is highly disturbed. Some of these X-ray features coincide with radio-detected structures, and that suggests giant shocks and turbulence being driven by mergers, either accelerating or at least re-accelerating electrons. And in the center of the cluster, some of these features may be caused by a merger of two small galaxy clusters, or the outburst produced by a supermassive black hole, or a combination of both. This is SpaceTime. Still to come, a new way to build the red planet Mars, and scientists find gold developing a new high-performance infrared nano antenna. All that and more still to come on SpaceTime. new study has discovered a surprising way planetary cores can be formed, and the findings could help reshape how scientists understand the early evolution of rocky terrestrial worlds like the red planet Mars. The new research, reported in the journal Nature Communications, offers the first direct experimental and geochemical evidence that molten sulfide, rather than metal, could percolate through solid rock and form a planetary core, and do so before the planet's silicate mantle begins to melt. See, for decades, astronomers thought that forming a planetary core required large-scale melting of a planetary body, followed by heavy metallistic elements sinking to the centre of the planet through a process called differentiation. However, this new study is suggesting a different scenario, especially relevant to planets forming further away from the Sun, places where sulfur and oxygen are more abundant than iron. In these volatile-rich environments, sulfur behaves a lot like road salt on an icy street. It lowers the melting point by reacting with metallic iron, forming iron sulfide so that it can migrate and combine into a core. See, until now, scientists didn't know if sulfide could travel through solid rock under realistic planetary formation conditions. The new results are giving scientists a way to directly observe this process using high-resolution 3D modelling, confirming long-standing models of how core formation can occur through a process of percolation, in which dense liquid sulfide travels through microscopic cracks in solid rock. The study's lead author, Sam Crosley from the University of Arizona in Tucson, says scientists could actually see in full 3D renderings how the sulfide melts were moving through an experimental sample, literally percolating in the cracks between other materials. It confirmed the hypothesis that in a planetary setting, these dense melts would migrate to the centre of a body forming a core even before the surrounding rock began to melt. The study's co-author, Scott Eckley from NASA's Johnson Space Center in Houston, Texas, developed high-resolution 3D renderings revealing melt pockets and flow pathways within the samples in microscopic detail. And these visualizations offer fresh insights into the physical behavior of materials during early core formation processes without destroying the sample. Of course, that alone couldn't confirm whether percolative core formation occurred over 4.5 billion years ago. For that, the authors turned to meteorites, looking for forensic chemical evidence for sulfide percolation. By partially melting synthetic sulfides infused with trace platinum group metals, they were able to reproduce the same unusual chemical patterns found in oxygen-rich meteorites, thereby providing strong evidence that sulfide percolation did occur under those conditions in the early solar system. To understand the distribution of trace elements, the authors developed a novel laser ablation technique which accurately measured platinum group metals which concentrate in sulfides and metals. The combined data provided powerful independent lines of evidence that molten sulfide had migrated and coalesced within a solid planetary interior, the first direct demonstration of this process in a laboratory setting. What this all means is that the study's offering a new lens through which to interpret planetary geochemistry. Mars in particular shows signs of one early core formation process. But the timelines often puzzled scientists. That's where these new results come in. They suggest that the Martian core may well have formed at an earlier stage, thanks to its sulfur-rich composition, potentially without requiring the full-scale melting that planet Earth experienced. In fact, this could help explain some long-standing puzzles in Mars's geochemical timeline and early differentiation. The results are also raising new questions about how scientists date core formation events using radiogenic isotopes such as hafnium and tungsten. See, if sulfur and oxygen are more abundant during a planet's formation, then certain elements may behave differently than expected, remaining in the mantle instead of the core and affecting the geochemical clocks used to estimate planetary timelines. This new research is advancing science's understanding of how planetary interiors can form under different chemical conditions, thereby offering new possibilities for interpreting the evolution of rocky bodies like Mars. This is SpaceTime. Still to come, scientists developed tiny gold antennas that will provide superior infrared observations. And later in the science report, the discovery of a new dinosaur species belonging to a new genus of Tyrannosauroid. All that and more still to come on SpaceTime. The advantage of infrared is that it allows astronomers to peer through the dust and gas that often cloaks the universe behind. Now, scientists have developed tiny gold antennas which can help cameras and sensors that see heat deliver clearer pictures of thermal infrared radiation for everything from stars and galaxies right through to people, buildings and items requiring security. Researchers with the US government's Sandia National Laboratories have developed a tiny nano-antenna-enabled detector that can boost the signal of a thermal infrared camera by up to 3 times, in the process improving image quality by reducing dark current, a major component of image noise, by up to 100 times. Sandia manager and nano-antenna project lead David Peters says thermal infrared cameras and sensors have existed for some 50 years now. But the traditional design of the detector that sits behind the camera's lens or a sensor's optical system seems to be reaching its performance limits. He says improved sensitivity in infrared detectors beyond what the typical design can now deliver is important both for national security uses and for use in science, especially astronomy research. The sensitivity and image quality of an infrared detector usually depends on a thick layer of detector material that absorbs incoming heat and turns that into an electrical signal that can be collected and turned into an image. The thickness of the detector layer determines how much heat can be absorbed and read by the camera. Trouble is that thickness has drawbacks. Peters says the detector material's always spontaneously creating electrons. These are collected and add to the noise in the image, thereby reducing image quality. And this phenomenon, known as dark current, increases along with the thickness of the detector material. In simple terms, the thicker the material is, the more noise the image is creating. So engineers have developed a new detector design that breaks away from relying on the thick layers, and instead uses a sub-wavelength nano-antenna, a patterned array of gold square or cross shapes, in order to concentrate the light on a thinner layer of detector material. In fact, this design uses just a fraction of a micron of detector material, whereas traditional thermal infrared detectors often have thicknesses of up to 10 microns. And for comparison, a human hair is about 75 microns thick. So the new nano-antenna's enhanced design will help detectors see more than 50% of an object's infrared radiation, while also reducing the image's distortion caused by dark current. Whereas current technologies can really only see about 25% of infrared radiation. It also allows for the invention of new detector concepts that simply aren't possible with existing technology. For example, by using nano-antennas, it'll be possible to dramatically expand the amount of information acquired in an image by exquisitely controlling the spectral response at the pixel level. And these new nano-antenna-enabled detectors can be made by simply slightly altering the usual processes for making an infrared detector. It all starts by growing the detector's material on top of a thin disc called a wafer. Then the detector material is flipped onto a layer of electronics that reads the signals collected by the nanometer antenna and the detector layer. Peters says after discarding the wafer, a tiny amount of gold is applied to create the patented nano antenna layer on top of the detector material.
This project was coming up with the next generation infrared focal plane array. What we were trying to do was increase the signal and decrease the dark current, which is a major component of noise in infrared detectors.
The noise in detectors scale with the thickness of your absorber, and so by thinning this absorber to actually slightly shorter than the diffusion length, you are reducing the noise associated or the dark current associated with that detector.
Infrared detectors have been around for 50 years. They've all used about the same architecture and used the same materials. We not only decided to look at a new material, but to change the architecture too.
And the way we've done that is take nano antennas, put them on the surface of that absorber, and those nano antennas concentrate the field at the surface of that detector and allows for a much higher quantum efficiency than you would normally see with a detector that thickness. The really amazing thing about the nano antenna enabled detector concept is that it can be applied to different detector types. So there's an opportunity for existing manufacturers to integrate this new technology with their existing detectors.
It was not a given that this was going to work. So that's why Sandia took it on. And now we're to the point where we have proven this concept, and this technology is ready to to be commercialized. So this is a perfect opportunity to show where the national labs can prove a concept and then spin it off to industry where it can be developed further.
That's Sandia manager and nano antenna project lead David Peters and team researcher Anna Truck-Pedretti. And this is SpaceTime. And time now to have another brief look at some of the other stories making news in science this week with a science report. A new study has confirmed that nanoplastics can disrupt the gut microbiome in mammals. A report in the journal Nature Communications has found that an accumulation of nanoplastics in intestines disrupted intestinal permeability and caused an imbalance in the gut microbiota. Nanoplastics are pieces of plastic less than 1,000 nanometers in diameter. That compares to microplastics, which are usually less than 5 millimeters in diameter. A new study has shown that a protein which gives fleas their bounce could be useful in stopping implant infections. A report in the journal Advances in Colloid and Interface Science claims lab tests are showing that resin mimetic proteins inhibit the spread of bacterial cells, preventing medical implant infection. The study is the first reported use of antibacterial coatings made from these proteins and is able to fully block bacteria from attaching to a surface. A re-examination of partial dinosaur skeletons found in Mongolia in the 1970s has revealed what is actually a new species of dinosaur belonging to a new genus of Tyrannosauroid. A report in the journal Nature claims the new Kankaloo genus is a smaller Tyrannosauroid dinosaur, similar to those that migrated from Asia to North America as the Eutyrannosaurines, the group which would eventually go on to produce the mighty Tyrannosaurus rex. Paleontologists say the lineage that went back to Asia formed two groups filling different ecological niches. Smaller mid-level and larger apex predators, with the latter returning to North America where the Tyrannosaurus emerged. Ireland's most haunted house, Loftus Hall, is up for sale. The place is so famous, haunted tours of the house have attracted thousands of visitors to the area, especially around Halloween. The mansion is the subject of various legends, including one in which the devil visited for a card game. The only problem is, Tim Mindham from Australian Skeptics points out, the building that's there now wasn't the original haunted house.
Loftus Hall is a big stately home in Ireland. It's touted as Ireland's most haunted house. It's a big house. The current owner had big plans of it. He was going to build a 56-bedroom hotel block, a gym, a spa, wedding facilities, 33 standalone garden cottages and 10 eco-pods. That fell through. So now he's trying to sell it. It's still a big house, 22 bedrooms.
You're saying he didn't have a ghost of a chance?
The house is famous particularly for a paranormal event where supposedly a stranger appeared at the door and he was invited in to play a game of cards, which is what you do when a stranger knocks at the door. And they played a game of cards and then he was happily playing away until one lady at the card table dropped a card, bent down to pick it up and noticed that this stranger had cloven hoof for feet. And said, and then the demon went, and then disappeared through the roof in a puff of smoke. So therefore they're saying, look, this famous haunted house, therefore had this famous meeting with the paranormal. The trouble is, it's not that house. That house was knocked down. Whoops. In the 1800s, in 1870, in fact, so was that 150 years ago. They built a house on top. So the house that's on top, which is this glamorous stately home, was dates from the late 1800s. So as the most haunted house, you could say it's the most haunted house site. It's not this house. Now, do ghosts continue even when the house is gone that they haunt? I don't know. And the one on top goes up. So anyway, if you're going to spend out of several million euros on this particular haunted house, don't look for the devil because it's the wrong place.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.